Now, as we discussed the equation for the COP of a reversed Brayton cycle and the assumptions which we have to take in the reversed Brayton cycle COP formula, we already discussed it. Now let us find out some of the very good observations from these equations and some of the observation based on the TS diagram of the reversed Brayton cycle. Now, let us say that first of all we know that the COP formula, COP of the reversed Brayton cycle will be 1 upon Rp raised to power gamma minus 1 upon gamma minus 1. This is the COP of the reversed Brayton cycle, and assumption is changes in kinetic energy 0, changes in potential energy 0, ideal gas, and gamma of expansion and gamma for compression is same. In these only we will be able to use this formula. And we know that from where this formula is derived, if you go back to your previous discussion, then we can say that the COP, if you revise the previous notes, that when we are deriving this will be come out from 1 upon T2 by T1 minus 1. T2 by T1 minus 1. Right, and T2 by T1 we are writing Rp raised to power gamma minus 1 upon gamma. And we know from the discussion that T2 by T1 is equal to T3 by T4. This we know. We already derived this if gamma C is equal to gamma E. Right, we know this. So in place of T2 by T1, I can write T3 by T4. So this COP will be equal to 1 upon T3 by T4 minus 1. So this COP will come out to be T4 divided by T3 minus T4. This is the COP of reversed Brayton cycle. Now, let us draw the TS diagram again. Let us draw the TS diagram for the reversed Brayton cycle again, because we need to compare this reversed Brayton cycle with the reversed Carnot cycle, which is the ideal cycle for the refrigeration system. We can say, let us say this is T and this is S, right? If I draw the temperature entropy diagram for this of a reversed Brayton cycle, it will look like this. We already see that. Just we are drawing the diagram again for your better understanding. Right. This is the diagram, TS diagram. This is process 1, 2, this is process 3, this is 3, and this is 4. Right, we already see this. 1, 2, 3 and 4. Now, the COP will be equal to T4 divided by T3 minus T4. Right. Now, if I take, let us say your assumption number 1, right? We are talking about the assumptions. Observation. Let us take for the first observation is, if I fix the heat rejection temperature, that is T3. T3 is the heat rejection temperature, and if I fix the refrigeration temperature, the refrigeration temperature is T1, right? The refrigeration temperature is T1. So we can say that first observation is, for a fixed heat rejection temperature at which the heat is rejecting, heat rejection temperature, that is T3, and fixed refrigeration temperature, fixed refrigeration temperature, that is T1. Right, you can understand that this T3 and T1 are fixed, not T2. T2 is depending upon the pressure ratio. How much you compress it, then T2 will increase. If the pressure ratio is more, this T2 is more, right? So the heat rejection temperature is T3, right? Because the condenser minimum temperature is T3, so this is the heat rejection temperature, and refrigeration temperature is T1, right? We have to store for T1. So if I fixed this T1 and T3, so we can say that if I fix this, then we can say that the COP of the Carnot cycle is more than the COP of the Brayton cycle. If I fixed this T1, this point T1 and T3 are fixed. If these 2 points are fixed, then we can say that COP of the Carnot cycle, reversed Carnot cycle, is greater than what? COP of reversed Brayton cycle. Reversed Brayton cycle. Or if you remove this reversed term, okay. COP of the Brayton cycle. COP of the Carnot cycle is more than the COP of the Brayton cycle. If I draw the Carnot cycle here, and you know that in the Carnot cycle, instead of these two constant pressure heat rejection process, we have two isothermal heat rejection process, and the temperature entropy diagram for the reversed Carnot cycle is a rectangle. It is a rectangle, right? Because the heat transfer process in that case is your constant temperature or isothermal process. So if I draw the Carnot cycle here, the Carnot cycle will look like this. This is process 1 to 2. So it will like this, because T1 and T3 are fixed. So let us say this is 4 dash, 3 is fixed. So if I draw a horizontal line from this 3, let us say it meets at this point. This is 2 dash. Right? Because 3 and 1 are fixed. Okay, we'll draw a this is point 2, and let us say, for your better understanding only, this diagram is important, that's why some accuracy must be there. Like this. This is point 1. So the process 1, 2 dash, 3, 4 dash, this is reversed Carnot cycle. So if I write that this cycle 1, 2, 3, 4, this is a Brayton cycle, and 1, 2 dash, 3, 4 dash, it is a Carnot cycle. It is a Carnot cycle. It is a rectangle, right? And what is the COP of this? If you write that here the lower temperature is T4 or T4 dash, you can say, and higher temperature is this T3. T3 and T2 dash are same, T4 dash and T1 are same. So what is the COP of this Carnot cycle? COP of a Carnot cycle is lower temperature divided by higher minus lower. So this will be equal to, COP of this will be equal to, I can write, this is, what is the lower temperature? Lower temperature is T4 dash, right? Lower temperature is T4 dash. So this is T4 dash divided by, in this case, higher temperature is T3. This is T3 minus T4 dash. This is the COP of this Carnot cycle, right? Lower temperature upon higher minus lower. And what is the COP of Brayton cycle? We know T4 upon T3 minus T4. This is T4 upon T3 minus T4. Right? T4 upon T3 minus T4. And from here you can observe this, that from here T4 is less than T4 dash. this T4 dash is more, T4 is less, T4 value is less, T3 is same, right? If this T4 dash is more, right, you know this from here, you can easily say that T4 dash is more than T4. T4 dash is more than T4, right? This is simple. This is T4 dash, this is T4. So if you see from here that if T4 dash is more than T4, T4 dash is more than T4, then this numerator is more than this numerator. If come out to be the denominator, T3 is same, T3 is same. If this T4 dash is more than T4, T4 dash is more than, this is minus sign, so this denominator is less than this denominator. Here T4 is less, so T3 minus T4 is more than the T3 minus T4 dash, right? So here the denominator is less, so this complete term T4 dash upon T3 minus T4 dash is more than, it is more than T4 upon T3 minus T4. Basic simple observation, simple mathematics. So we can say that for a fixed T3 and T1, the COP of a Carnot cycle is more than the COP of a Brayton cycle. And also we can say that COP of this Brayton cycle, second thing, that COP of the Brayton cycle will be equal to COP of the Carnot cycle if this T1 and T4 are same. If this T1 and T4 are same, right? If this T1 and T4 are same, that is in the straight line, so then we can say that COP of the Brayton cycle will approach the COP of the Carnot cycle. So second observation we can write in this case, we can say that COP of Brayton cycle approaches COP of Carnot cycle when T1 is almost equal to T4. When this T1 approaches T4, when this T1 is approximately equal to T4, so this will be this kind of a line. So in that case only this Brayton cycle COP will approach to the COP of the Carnot cycle. Now, what is the disadvantages when this T1 approaches T4? Okay, T1 is and T4, if let us say T1 and T4 will be equal, then you can see that from the previous discussion that refrigeration effect in case of Brayton cycle come out to be Cp into T1 minus T4. Cp into T1 minus T4. This is the refrigeration effect, right? Heat supply. So if T1 and T4 are equal, then this will be 0. So the refrigeration effect is 0. That means that if the Brayton cycle will approach to the Carnot cycle, its refrigerating effect is 0. It will not give you this refrigerating effect is what? It is the desired effect. That's why we are using Brayton cycle, right? That's why we are using this device, this refrigeration cycle. If the desired effect, what we want, is not there, then what is the use of this refrigeration cycle? So this is the thing. If COP approaches the Brayton cycle, then we can say, then COP of Brayton approaches COP of Carnot. In that case, refrigeration effect will be 0. So there is no use to use this refrigeration cycle. This is the limitation with the Brayton cycle, right? That's why, and we know that between the same temperature limits, COP of Carnot will be maximum than the COP of the Brayton cycle. Third one is that COP of reversed Brayton cycle, COP of a reversed Brayton cycle is a function of pressure ratio. You can see from here, it is a function of pressure ratio. And we can say that if this pressure ratio increases, RP, if RP is increasing, this is increasing, so this denominator is increasing, so COP will reduce. COP will reduce. Is a function of pressure ratio, and COP will reduce or COP will decrease. You can write like this: COP will decrease with increase of pressure ratio. With increase of pressure ratio. COP will decrease with increase of pressure ratio, and we can say when the pressure ratio is equal to, if pressure ratio will be equal to 1, right? If there is no compressor, okay, COP will be infinity. Let us leave it, right? So this is the thing. So if I can write, if I draw this a graph between COP and pressure ratio, it will be like this. It will be like this. It will be like this, and it is asymptotic, and this COP will be like this, and when the pressure ratio will be 1, then COP will be your infinity, right? So this is the graph of COP versus pressure ratio. If COP is increasing, then if pressure ratio is increasing, then COP will decrease, right? It depends on the pressure ratio only. There is only one view, or you can write here that COP of a reverse Brayton cycle is a function of pressure ratio only, right? Gamma is a constant. So COP of a reverse Brayton cycle is a function of pressure ratio only, and if pressure ratio increasing, then COP will decrease. So these are some of the important observations which we can study of the reversed Brayton cycle, that what is the effect of COP and how the Carnot cycle is differ from the Brayton cycle.